First of all, welcome to all of you. It's really great to see all of you here on Candidates Friday. I know that you are all looking at multiple opportunities, and I'm hoping that all of you have a really good experience today at UMass, get a feel for everything that is going on here, and in the end, actually decide to come here. So let me introduce myself first. I'm Prashant Shenoy. I'm a faculty member here in the college and also the Associate Dean for Computing. So what I'm going to do for the next 20 minutes or so is tell all of you a little bit about the research that's going on here in the field of sustainability and computing. Now, this may be a area that you've not heard about much. The sustainability and computing is a relatively new area within the field of computer science. So what I would like to do is give all of you first a very high level, broad overview of what this field is about. And then I can tell you all a bit about the research that's going on at UMass, both within my group as well as in the labs of other faculty members here, but who are not going to be able to speak today. So let me start with a very high level motivation for all of this research. So the sustainability research is driven primarily by climate change. And we've been hearing a lot in the news in recent years about all kinds of extreme weather events that are getting worse as a result of climate change. So here are some pictures of flooding that has been seen in recent years, wildfires in California, tornadoes and hurricanes that are becoming increasingly common. So many of these events were at one point thought to be once in 100-year type weather event, but we are now seeing them every few years as a result of acceleration in climate change. So there's been, of course, lots of talk also about how best to address climate change issues. And by and large, this requires that our societies as a whole think about decarbonizing and reducing carbon emissions, which are the primary source of all of this climate change. So the graph here shows the red curve there shows that if nothing is done, then temperatures are going to rise by about 5 degrees Celsius by the end of the century due to all of the greenhouse gases, including CO2, and that's going to have catastrophic consequences. And if we hold emissions to maybe 1990 levels, then you are at the blue curve where temperatures rise at by 1.5 degrees Celsius, which is thought to be manageable in terms of its impacts. Now, since the goal broadly for sustainability has to be on decarbonization, it's instructive to understand what decarbonization means for fields that we are familiar with. So let's talk about computing. Okay, we are all computer scientists, and so it's instructive to think about what kind of carbon impact we are having as a field. So let's think about computing infrastructure. Right. So as a field, we have been extremely successful. The internet has really revolutionized everything that we do today. Mobile devices and smartphones are everywhere. Cloud computing is driving a lot of the applications that you see everywhere. So this has become the defining trend of our time, the technology trend of our time. But the success also comes at a high cost, and one of that is shown by the graph at the bottom left, and that's essentially just the growth over the years in the number of cloud servers that have been deployed across the globe. And you'll see that there is, by and large, exponential growth in the number of servers. Now, servers have to be powered, and the electricity that is consumed by the servers does have a carbon cost, because generating that electricity results in carbon emissions. So as a result, cloud computing, as well as all the other infrastructure, the internet and mobile computing and devices and laptops, they generate carbon emissions that is continuing to grow over time. And just as one example, because many of you may be interested in AI. Let's think about the carbon impact of AI workloads, right? So the graph on the bottom right shows you the size of deep learning models in NLP and computer vision and all other fields of AI over the years. And that's on the y-axis is the size of the model in log scale. The x-axis is years, and you see that that's a linear line, which in log scale, which essentially means that the size of these models are actually increasing at an exponential rate. And in fact, if you look at these trends, you will see that machine learning and deep learning workloads are doubling every 3.4 months, right? So every quarter, the workload that are seen on the cloud platforms is actually twice of what it was before. So that's a very high rate of exponential growth. And clearly, this kind of growth cannot be met with current infrastructure. And if you think about its carbon impact, this is going to have increasingly high growth in energy consumption of the cloud and increasing carbon usage. So there is, of course, this negative implication of all the success we've had as a field, both in cloud computing and AI and so on. Now, thinking more broadly in terms of decarbonization, let's think about where else do carbon emissions come from. Now, even though the picture I presented on the previous slide for computing as a field seems like a big problem, if you think about the broader picture, the global carbon emissions from all of computing infrastructure is actually less than 5% today. And in fact, if you look at that pie chart that you have on the bottom left, it is in the other category, which is in sort of the 9% category. So there are other really big emitters of carbon. This includes buildings, which are around 40% of the total carbon emissions. These are the homes we live in, the buildings we work in, and so on. And those are a big generator of carbon because they consume electricity. And transportation is another large component, 22%, and industry, 30%. So even though there is a lot of interesting things you can do to make computing greener, there are even bigger problems to tackle if you want to really think about climate change, which is to address all of these other sectors as well. Okay. So with that very brief overview, the broad research agenda in this field of sustainability and computing is to think about how can computer science and computing techniques help with decarbonizing computing and physical infrastructure. And I will explain what decarbonizing means from a computing standpoint. Okay, and before I proceed, I do want to mention that our college has a mission, which essentially is shown at the bottom there, which is computing for the common good. You probably heard about this earlier today. You might hear about this over and over again. This is what sets UMass and UMass computer science apart from many other computing programs, which is to use our research and technologies in a way that is going to help society and for the common good. And the research that we are pursuing in the context of sustainability is really aligned with that mission of computing for the common good. So let me now tell you all a little bit about how can we design computer science techniques to decarbonize either computing itself or decarbonize AI or physical infrastructure. So first, I'm going to talk about a project called Carbon First, and the goal of which is to make cloud computing zero carbon. So you want to take all of cloud infrastructure and you want to decarbonize it and essentially make its carbon footprint go to zero. And this really requires a change in how we design computing systems as a whole, because typically when you try to write a program or design a system, you want it to perform well, you want it to go faster, you want it to be reliable. Rarely do you think about, I want it to actually consume less carbon. So you want carbon awareness to be a design goal in designing any software and hardware and any technique or any algorithm you design. And so that's really the broad goal of this project. But in terms of one nugget as to how you could go about doing this, let's take a look at the figure at the bottom left, which is a global map of electricity generation in different parts of the world and how green that electricity is. And the basic idea is if your electricity comes from wind, solar, hydro, it has low carbon footprint. But if you're using coal and natural gas, your electricity is going to have high carbon footprint. And so the green region show places where your green generation, and the yellow and brown say as the electricity gets increasingly carbon intensive. That's basically the meaning of those color codes. So what this is saying is, if you consume electricity in different parts of the world, it's going to generate different amount of emissions. Okay. Now, the figure on the right shows you Amazon's cloud infrastructure. Okay. So what, and you'll see that it has data centers all around the world. So what this tells us is that if your computing application has flexibility in where it can run, then it is better to run it in cloud regions where the electricity generation is green, because you might do the same computation, but it's going to have lower carbon emissions over running it in regions where the electricity is brown, where the same computation will cost more in terms of carbon impact. So the goal of the research that we are pursuing is to think about broad load balancing, scheduling, and distributed application design, where you can monitor the carbon cost of electricity in different parts of the world and direct your workload to cloud regions where the electricity is green. And this map is not going to stay static, incidentally. It's going to change over time as solar and wind generation changes. So you want to keep reacting to these changes by moving your workloads to where electricity is the greenest. And that's one type of research that we are pursuing here. And let me now explain a different approach to doing something like this. And here I'm going to talk about decarbonizing AI, or a field that is referred to as green machine learning. So as I already said, machine learning computations have a significant carbon impact. So you want to continue to develop new AI techniques, but we want to make sure that they are green and have low carbon impact. So how can we do this? So to understand that, let's take a look at the graph again at the bottom left. And that graph shows you the carbon cost of electricity in a particular region. The black one says South Australia, the red one is Ontario, Canada, and so on. And what you will see is that the carbon cost of electricity in any region is itself varying over time. There are times of the day when the carbon cost is low. This is when the wind is blowing or the sun is shining, so you have lots of clean renewables. And maybe when that's not the case, the carbon cost goes up because you rely on coal and natural gas and so on. So our goal here is to design intelligent machine learning training frameworks that can take this information into account and try to shift computations, training computations, to time periods where the carbon cost is low. So these are scheduling approaches where you will schedule more computations in low carbon periods and higher and fewer computations in high carbon periods, and thereby reduce the total carbon emissions from your training process. And that's shown in the graph in the right, where the red curve is essentially the carbon intensity of electricity. The black curve is actually showing how your machine learning training is adapting to the changing cost of carbon and changing the amount of computations performed in each time period. And just by doing the simple changes, you can reduce the carbon cost of your machine learning training by 45%. Okay, and this is just an initial result. There is a lot more you can do to reduce it even further. Okay. So let me now talk about how to decarbonize physical infrastructure. So the previous two slides gave you some sense of how you can make computing or AI green. But now let's think about how can you make other things greener, and in particular, how can we make buildings greener. So here we have a project that has been looking at how to think about replacing the natural gas heating that is used by many of the buildings and homes, and replace that with electric heating that is more efficient and also can use green energy. And that's going to reduce the carbon emissions from heating your homes in the winter. And what we have done is develop Bayesian models of a building energy usage, and use these models to analyze how efficient a home or a building is, and to compare those homes across the peer groups using models for each home that are shown in that picture that you see at the bottom. And the idea is to compare homes across within rather each peer group and find the least efficient buildings that you can find. And those are good candidates for changing the natural gas heating to more energy efficient electric heating, which gives you the most reduction in carbon emission, because you can take the most inefficient buildings and make them more efficient, and that will give you higher carbon savings. So these techniques use a combination of Bayesian models and optimization to essentially come up with a plan to decarbonize buildings by making appropriate energy retrofits. So this is an example of how computing techniques can help you make buildings greener. It may not be something that you thought computer science could help with, but there are people both here at UMass and elsewhere who work on these types of problems. Okay. The last thing I'm going to say and then conclude is another project called Deep Roof, which uses computer vision techniques to essentially decarbonize energy. The idea here is to increase the amount of solar energy that is used to produce electricity for homes. And in most cases, you can think about putting these solar panels on roofs of buildings and homes. If you are actually here on campus, you will find out that the computer science building, which is one of the two buildings we are in, actually has a solar roof. There is a whole set of solar arrays that been put on the roof of the building. So lots of our energy is generated locally and is being used from the solar arrays. So thinking more broadly, you can ask, what are good rooftops on which we can deploy these solar arrays so that more and more energy generation comes from clean sources, and there's less and less reliance on natural gas and coal and other sources of electricity. So what we did is we looked at satellite images that you can see in sites like Google Maps. We change to satellite view, you see aerial images of buildings, and that's what is shown on the picture on the left. And we fed these images to a trained computer vision model, and say which essentially goes and looks for rooftops. So it'll identify roofs that it sees, and then it will analyze these roofs based on its orientation and pitch, and then figure out whether these buildings and their roofs are good candidates for solar arrays. So if you have a good south-facing roof that does not have trees around the homes, then you can make that a good candidate for solar deployment. On the other hand, if the orientation is not right or there are too many obstructions, that's not where you should put a solar array. So you can automate this process and analyze very large amounts of data at scale using this computer vision technique, and figure out very quickly all the buildings in a city that could be good candidates for deploying solar arrays. And then you can do these installations at scale and then try to reduce the carbon consumption of energy for an entire city. So here's an example of use of computer vision techniques to solve an interesting energy and decarbonization problem. So before I wrap up, I want to mention that that the sustainability research that is going on here is actually a part of a much larger group of faculty members who all work on these problems. So there are listed 5 of us here. Muhammad Hajjasmaili, who is an assistant professor here, Ramesh Sitaraman, who is a professor. Then there's David Irwin and Jay Taneja, who are adjunct faculty members from computer engineering, and myself. So there are 5 of us who work on these problems. These problems span systems, theory, and AI. This is not just a systems problem or a theory problem or AI. We bring a range of techniques to address these problems. And then there is a much broader group here called Elevate that spans many departments: engineering, social sciences, econ, and many others. And we all work together on these problems from many different angles, because it's not that computer science is going to solve all of these problems. And there are many different perspectives we have to bring to this problem. And we have a group called Elevate that's looking at energy transition, and equity aspects, and energy justice as well. So with that, I hope I have convinced you of 2 things. First is that sustainability and computing is an interesting and important area of research within computer science. And the second is that UMass is a great place to do this type of research. And there's a substantive group here and one of the best in the country, I would say, that's actually looking at these kinds of problems. So with that, I'm going to end it here. I'm just about out of time, so I'm happy to take a question or two before we conclude. Yes.
So really awesome presentation. Thank you for sharing this. I had a quick question about kind of what our impact is, or what I should say the students at Amherst's impact is, in terms of like what kind of computing resources do the AI students use at Amherst, and are they green, or is there processes to make them more green, or kind of like what does that look like right now as far as the impact of the university goes?
And that's a good question. So I'll answer that quickly in two different ways. So first of all, the college has a large GPU cluster. Okay. It's one of the largest in the country in terms of a university GPU cluster's name is Gypsum. So if you come here and start doing AI research, you have plenty of resources in terms of GPU machines to do your research. That's the good part. The not so great part is, of course, these machines consume a lot of electricity, so it does have a carbon impact. But fortunately, what the university has done, and the faculty in computer science had a great deal of influence on it, was to build a very green data center. So there is a high performance data center that's in Holyoke. Its name is MGHPCC. It's the only LEED platinum data center run by universities in the country. A lot of its energy comes from clean hydro, because Holyoke is a town that generates lots of hydro. So the carbon impact of that energy consumption is already low, because we put our machines in a neighboring town that generates a lot of clean hydroelectricity. So you can be rest assured that all of your AI computations are actually going to not have a big carbon impact, unlike elsewhere. Any other questions before I hand it back to Taylor? Okay, thank you very much for listening, and I hope all of you have a really great rest of your day and get to experience everything our college has to offer.